Good morning. Let us start today's discussion with elastic waves. So, this picture over here shows you a rod made up of elastic substance. The length of the rod extends in this direction, and the cross section of the rod has an area A, and the length of the rod is in this direction. And the situation that we are interested in is where we have introduced a disturbance in this rod. For example, let me just give you an example. Think of this as the rod, as the rod in which you wish to study disturbances. So, this is the elastic rod, and I put in a disturbance like this. So, I tap it in one end, and if I tap it at one end, it will cause a compression over here. This compression will then is a disturbance which I have introduced in this elastic rod, and the question that we are interested in is what happens to this disturbance. How does this disturbance evolve? So, the picture over here shows you the section. Let me so what we do is what we have done is that we draw lines at equal spacing in this direction. I should first tell you that we are interested in disturbances which are there along this direction only. So, to start with, we shall discuss a situation where the disturbance is such that it varies only in this direction. It does not vary along the two other directions, and we shall refer to this direction as the x axis. The length of the rod, the x axis is along the length of the rod. The y and z axis are along these other two directions in which the disturbance, we are not interested in the variation of the disturbance in these two directions. For the time being, we assume that the disturbance does not vary in the other two directions, it only varies in this direction, and we have drawn lines at equal x intervals over here. And this picture shows us these lines at equal x interval drawn along the elastic rod in the situation when the rod is undisturbed. Now, when I introduce a disturbance in the rod, the disturbance compresses certain regions and it causes rarefaction in other regions. So, this shows you a particular disturbance. This particular disturbance is such that it causes the first element over here, so it causes this element over here along the length of the rod to get compressed. So, the first element over here has now got compressed because of the disturbance, and it is only this much. The second element has got rarefied, so it covers a larger length than it originally was. The third element is compressed, the fourth element is compressed, the fifth element again is rarefied, the sixth element is more or less the same, maybe a little compressed, and this is compressed. So, so what I have shown you here is that we have drawn lines at equal interval along this direction of the rod, and because of the disturbance that we have introduced, possibly by tapping it at one end or whatever means, these lines have got moved around and the different elements have got compressed or rarefied. So, let us now focus our attention on the element over here. So, I had drawn the line on the element over here. As a consequence of the disturbance, this gets shifted to a new position, and the deformation of this element. So, this piece over here, this element over here has got deformed to a new position, and the deformation we denote by xi x. So, the element of the rod which was at x earlier has now shifted to a position which is x plus xi of x. So, the element which was at x earlier, this particular element which was at x earlier has now shifted to a new position which is x plus xi of x, and in this particular case it has shifted to the left. So, xi of x is negative. This particular element is at a different value of x and it has got shifted to a new position over here, and for this particular element the xi of x, the displacement is positive. So, xi of x is a function which tells me the displacement at any value of x at any point x, and it will vary, in general it will vary with the value of x. Now, we are interested in studying how this whole disturbance pattern evolves. The disturbance pattern is quantified through this variable xi of x, which tells me how each element, the displacement of each element, and we are interested in studying how this evolves. So, before getting into this, let me now briefly recapitulate some of the properties of an elastic rod, what we mean by elasticity. So, let me recapitulate briefly what exactly do we mean by elasticity. So, this picture shows you a bit of an elastic medium. The cross sectional area of this medium is A. So, this is the cross sectional area of it is A, and the medium, the elastic substance that we are interested in has a length L, cross sectional area A. Now, there are two quantities which are defined in elasticity. One is called the stress, the other is called the strain. The stress is the force per unit area. So, if you apply a force on this surface over here, or conversely, if you extend this element, by an amount xi. So, if you extend this element by an amount xi is the deformation of this element. So, the length which was originally L has now become L plus xi. The ratio of the deformation to the original length is called the strain. So, this ratio of the deformation here is xi divided by the original length L. So, the original length of this elastic substance was L, it has got deformed, we have pulled it so as to make its length larger, and the amount by which the length has got elongated is xi. The ratio of the deformation xi divided by the length is referred to as the strain. And if you pull this, so if you elongate this elastic substance by pulling it, if you elongate an elastic substance, a force will develop which will oppose the elongation. So, a force will develop in the opposite direction, and we define the stress as the force per unit area. So, if you deform this elastic substance by elongating it in this direction, a force will develop, and the force per unit area is what we refer to as the stress. And for an elastic substance, the ratio of the stress, force per unit area, and the strain is a constant which depends only on the properties of the material. So, depending on the material, the ratio of the stress divided by the strain, will be a constant called the Young's modulus. And this is a property of the material of which the which the rod is made up. So, for every elastic substance there will be a different value of the Young's modulus, and the stress and the strain are related in a linear fashion through the Young's modulus. They are proportional to each other through the Young's modulus. So, what we see is that if I deform for an elastic body, if I deform it by an amount xi, there will be a force produced, and the ratio of the stress to the strain is a constant value, which is and the value of this constant depends on the medium that we have chosen, the medium of which this rod is made up. So, this basically tells us that the force that will be developed if I elongate this rod, if I deform this rod, the force that is going to develop is proportional to the displacement, to the deformation of the rod, which is what we have here, and the constant which relates the force to the deformation xi is, we arrive at this constant through the fact that the stress divided by the strain is the Young's modulus. So, it tells us that the constant relating the force which develops if I deform this object by a length xi, this constant is the Young's modulus into the cross sectional area divided by the undeformed length of this object. So, the point which I am trying to make over here is that we can, an elastic material, this is an elastic rod of cross sectional area A and of material whose Young's modulus is y, and it has a deformed undeformed length L. We can think of this as a spring. We know that for a spring, if I pull this end of the spring over here by an amount xi, then there is going to be a force developed which is going to oppose this elongation. So, the force is going to act in the opposite direction. If I have elongated it, the force is going to try and push it back to its original position. And for a spring, the relation between this force and the deformation is through the spring constant K. And if the deformation is applied to a solid elastic object like this, then we can think of this as a spring whose spring constant K, so the point is that we can think of this solid as in terms of a spring of spring constant K, which is equal to the Young's modulus y into the cross sectional area divided by the undeformed length. Let me repeat again. So, if I have an elastic object, elastic body of cross sectional area A, Young's modulus y and undeformed length L, I can think of this as a spring of spring constant y A by L. So, if I introduce an elongation xi, so I pull this, so I deform this by an amount xi, then there is going to be a force developed which is going to oppose this deformation, and the force is the spring constant which is y A by L into the deformation. So, this acts like a spring as far as deformations in this direction is concerned. So, let us now go back to with this brief review of elasticity, let us go back to the problem which we were discussing. The problem which we were discussing, we had an elastic rod. In this elastic rod, we had disturbances. And in order to study these disturbances, the disturbance varies only in this direction, the disturbance is only along this direction, and it only varies in this direction also. So, in order to study this disturbance, we had divided the rod into slabs. So, we had divided it into slabs like this. So, this is one slab, and I shall be showing only the cross sectional view over here. So, we have labeled this direction with the x axis and we have divided it into slabs of equal interval delta x. and we shall focus our attention on a particular slab. So, we shall choose a particular slab and focus our attention on it. So, we shall look at this particular slab over here, this particular slab, and focus our attention on this. So, this shows you a magnified view of that particular slab which extends from x to x plus delta x. So, let us ask the question, what is the mass? What is the mass of this slab? What is the mass of this element which extends from x to x plus delta x? So, if let us first calculate the length. The length of this is delta x, and it has a cross sectional area A which I have not shown, and it has a if the whole medium has a undisturbed density rho, then the mass of this element is delta x into A, the cross sectional area, which I have not shown in this figure, into the density of this material, which is rho. And the mass into the acceleration. So, what is the next question is, what is the acceleration of this element? Now, each point over here, because of the disturbance, will get deformed. So, the point x will move to a point x plus xi xt, that is the displaced under the deformation, under the disturbance, the mass which was at the point x here will move to a different point x plus xi xt. So, it will move to a different point where the difference is xi xt. Now, the question is, what is the acceleration? So, you see, if you ask the question what is the velocity, it is going to be the rate of change of xi with respect to time, and the acceleration is going to be the second derivative of xi with respect to time. So, the acceleration is del xi del t square, this of xi x t. So, this is the mass. So, if we focus our attention on this particular element of that elastic medium, the mass of this element is delta x a rho, and the acceleration is del square xi del t square, the second partial derivative with respect to time of the displacement xi. So, the mass into the acceleration should be equal to the total force sum of the total forces acting on this element. So, let me write it down and preserve it for later use. So, we have calculated the mass into the acceleration acting on that particular element, and we see that it is the mass is delta x into a into rho this is the mass into acceleration for the element which we are focusing on, for the mass element in the slab, the mass element in the rod which we are focusing on, and mass into acceleration should be equal to the total force acting on that element. So, we have to now calculate the total force which is acting on that element. Let us now discuss how to calculate the total force acting on the element. So, we are focusing on this particular mass element, and there is going to be a force on this particular mass element. One force is going to arise from the deformation of the element of the elastic rod which is to its left. Another force is going to arise from the deformation of the element which is on its right. So, let us first consider the element which is on its left. Let us consider this element over here. We can think of this element as a spring. I just told you a short while ago that we can think of the deformation of each of these elements as that of a spring. So, under the disturbance, this point x minus delta x gets shifted to a point x. Let me write it for you here. So, the point x minus delta x gets shifted to a point x minus delta x minus rather plus xi at the point x minus delta x. There is a t also which I have not shown explicitly. So, the deformation of this point is originally in the undisturbed situation, this point is at x, this point corresponds to x minus delta x. Because of the disturbance, it goes over to x minus delta x plus xi x minus delta x. That is the deformation of this particular point. Now, what is the deformation of the other end of the spring? You see, we are thinking of this as a spring, which I have shown over here. This end of the spring originally at x now goes to x plus xi x over here. So, if I now want to find what is the deformation of the deformation of the spring, the deformation of the spring is the difference between this and this. So, the force which is going to develop because of the deformation of this is going to be, so the force which is going to develop from the spring on the left, the force which is going to develop from the spring on the left there is going to be a force which is going to develop. The force from the spring on the left is going to be proportional to the change in the length of the spring. The change in the length of the spring is the original length is delta x, the change in the length is the difference between this and this. So, the force is going to be minus k into xi x minus xi x minus delta x right. So, this is the deformation of the spring. The left tip of the spring gets displaced to xi x minus delta x, the right tip gets displaced to xi x by an amount xi x. So, the total deformation of the spring is the difference between these two, and there is going to be a force which is going to be opposite to this deformation, which is the force due to the spring on the left, which is what I have shown over here. Now, the spring constant k for this element, we have already determined that the spring constant A is y into the cross sectional area divided by the length, the undisturbed length of this element. So, this is the element that we have replaced by this spring, its undisturbed length is delta x. So, this is going to be y a by delta x into this factor xi x minus xi x minus delta x. So, we can calculate the force on the left. The force on the left is this whole thing over here, and if I look at the ratio of xi x minus delta x divided by delta x, that is the derivative of xi x at the point of the function xi at the point x. So, what we see is that the force from the left, is equal to minus a, the cross sectional area, into the Young's modulus into del by del x of xi x t. So, the ratio of this difference divided by delta x is the derivative of xi at the point x, which is what we have replaced over here. So, we have calculated the force due to the spring on the left, and that is proportional to the derivative of xi at the point, at this point over here. Now, let us calculate the force due to the spring on the right. The spring on the right is, so we have represented this elastic, this bit of the elastic material on the right as a spring over here, and there is going to be a force. So, if I displace this point and if I displace this point, the difference between these two displacements, the displacement of this point is xi x plus delta x, the displacement of the other tip of the spring is xi x plus 2 delta x. The difference between these two displacements is going to give a force which is going to act on this. How much is the force which is going to act from the right? Let me now focus on that. The force which is going to act from the right so if I push this element of the spring onto the right, the force that develops is going to be to the left, which tells us that the force from the right is going to be minus k into xi x plus delta x. This is the force that arises when I push this tip to the right or to the left. There is also going to be a force when I push this force. If I pull this end of the spring over here, if I pull this point over here, elongate it like this, it is going to give a force in this direction on this end, So, we can say that the force arising due to the displacement of this end of the spring is going to be this minus xi x plus 2 delta x. And again we can write the spring constant in terms of the Young's modulus, the cross sectional area divided by delta x, and we have the difference between these two. Which gives us, again you take this minus this divide by delta x, and in this case you get a extra negative sign because so what you have is this is equal to y a del by del x Okay, so we have written the force both on the left hand side and on the right hand side in terms of derivatives. The force on the left hand side involves the derivative at this point. The force from the right hand side involves the derivative at this point. To calculate the total force on this mass element which we were focusing on, we have to add up both of these. So, the total force F is equal to the force from the left plus the force from the right, and this is equal to y a, the cross sectional area A. So, let me show you the expressions again. So, we have to add up this and this, and this is equal to y a xi x plus delta x minus xi x. This is the force from the right, this is the force from the left, and there is the derivative of both of these del del x del del x. This is the force from the right, this is the force from the left. We can write this as y a del del x xi x plus delta x minus xi x, and this difference we can write as y a del del x. This difference we can write as delta x into the derivative of xi with respect to x, keeping only the first order term. So, what we see is that the force is the second spatial derivative of xi with a factor of delta x going out. So, the total force due to the two elements on the two sides, total force is y a delta x into the second derivative of xi. Now, we had right in the beginning calculated the mass into the acceleration, and that had come out to be this. So, now we can equate it to the total force which we have just calculated, and we see that the factor of delta x cancels out, a cancels out, and we have an equation. Let me write down the equation for you here. The equation that we have is the Young's modulus del square del x square xi is equal to the density into the time derivative of xi, second time derivative of xi. This equation can be written as follows. So, let me just rearrange the terms in this equation. This equation can be written as del xi del x square minus 1 by C s square del xi del t square. This is equal to 0, where this constant C s in this case you can identify what it is. So, we have you have to bring the y over here, and then you can write C s, you can identify C s with the ratio of rho and y. So, C s is y divided by rho, the square root of this. So, we have written this equation in this form, where this we have introduced this constant C s, whose value whose significance we shall discuss shortly. C s is the ratio of the Young's modulus to the density of the material. Now, until now we have been discussing a situation where we have a disturbance which is there only in the along the x axis. We have not considered what happens to the disturbance along the y or z axis. We can easily generalize the whole discussion now to a situation where the disturbance propagates along all three directions, along x, y and z. So, if you have a disturbance which is there along all three directions, along x, y and z, you have to replace the spatial derivatives with respect to x with spatial now you have to replace it with some combination of spatial derivatives with respect to all three directions. So, let me now tell you what you have to do in case you we have a disturbance which propagates in all three directions. You see, there is a spatial derivative with respect to x, xi is a function of x alone, and we have a spatial derivative with respect to x. We have to now replace this del x square, the second partial derivative with respect to x. We have to now replace this with del x square plus del y square plus del z. So, partial derivative with respect to x square now gets replaced by the partial derivative with respect to x square plus the derivative with respect to y, the square of that, plus the partial derivative with respect to z, the square of this. This combination of partial derivatives of x, y and z is a very important operator, which is referred to as the Laplacian, and it is denoted by this symbol over here. This is called the Laplacian operator. And the equation that we had earlier, the equation that we had derived for the disturbance in that solid, in that elastic solid, in the situation where the disturbance can propagate along all three directions, this can be written as the Laplacian del square xi. Xi is now a function of r and t, the vector r and t. It can vary in all possible directions. The rest of the equation remains unchanged. So, let me write down the rest of the equation, show you the rest of the equation. We have minus 1 by Cs square into the partial derivative, second partial derivative. So, that remains unchanged. So, this is the most general equation that you could have for the disturbance, where the disturbance is now free to propagate in all three directions x, y and z, which we denote by this vector r. This equation is called the wave equation, three dimensional wave equation. This is called the wave equation. This equation is the wave equation. So, if we have a wave which can propagate in all three directions, three dimensional situation, this is the wave equation. In the situation where it is only one dimensional, this is the wave equation. Okay. So, what we see is that the evolution of disturbances in that elastic solid. So, we have a solid which is made up of some kind of an elastic material, you put a disturbance in that elastic material, the disturbance, the evolution of that disturbance in the elastic medium is governed by the wave equation. Okay, so, this is the first thing that we see. Now, let us look a little closer at the wave equation. The wave equation, as we have derived it, has one constant, it is called Cs, which in this, for this particular situation where we have elastic waves, the constant Cs is the square root of the ratio of the Young's modulus divided by the density of the medium. Now, let us look at this equation a little closely. So, the first thing that we can do is we can ask, is the plane wave, which we have discussed quite extensively earlier in this course. So, the plane wave xi solution xi r t is a constant A, which is not very important, amplitude, constant amplitude. We are working in the complex notation, let me remind you. So, we are going to look at a particular solution which we have already discussed, which is the plane wave solution e to the power I omega t minus k dot r. So, we have already studied this represents a plane wave. Let us check if this plane wave is a solution to this wave equation that we have just derived. Okay. The plane wave which we have studied has a few unknown constants, few constants. So, this A is the amplitude of the plane wave. It has, in the complex notation, it has both the amplitude and part of the phase. Omega is the angular frequency of the plane wave. It tells me how fast, if I sit at a particular position, it will tell us how fast it changes with time, how fast the disturbance changes with time. K is the wave vector. It has both the information about the direction in which the wave is propagating. It also tells us that at a fixed time, after what distance the wave will repeat, what is the wavelength. It also tells us the direction in which the wave is propagating. Now, let us check if this is actually whether this is a solution to the wave equation which we have just derived. This wave equation governs the evolution of disturbances in that elastic solid. So, let us first calculate the time derivative of this function. If I differentiate xi with respect to time once, you basically differentiate the e to the power I omega t with respect to time. If you differentiate an exponential, you recovered an exponential with a factor So, if I differentiate this function with respect to time, what I recover is I omega into xi, right. So, differentiating this with time with respect to time once brings out a factor of I omega, and we have the xi again, right, that is obvious. So, if I differentiate it twice with respect to xi, we get one more factor of I omega. So, we will have I omega square xi, which is minus omega square xi. So, what we see is that if I differentiate it with respect to time, if I differentiate this particular plane wave solution, plane wave which we are trying to see whether it is a solution or not, if we differentiate this form of xi twice with respect to time, it is equivalent to multiplying it with a factor of minus omega square. Similarly, we have to also consider the action of the Laplacian operator on this function's xi. Now, the Laplacian operator has two derivatives with respect to x, two derivatives with respect to y, and two derivatives with respect to z. If we differentiate this with respect to x, what happens? That is the question. Okay. Now, remember that the wave vector k will have three components, kx, ky, and kz. If I differentiate this with respect to x twice, so let me write it down straight away without doing the algebra, del x square xi is going to be, you see, if you differentiate once, you will get a factor of I into kx, where kx is the x component of this vector k. So, if I differentiate it twice, I am going to get minus kx square xi, just like if I differentiate with respect to time. Similarly, if I differentiate with respect to y twice, I will get ky square. If I differentiate with respect to z, I will get kz square. So, what we can say straight away is that the Laplacian of xi is going to be minus k square xi, where k is the modulus of this wave vector. K is the wave vector dot with itself. Okay. So, it is quite clear from this that the Laplacian acting on this xi, which the Laplacian is the sum of derivatives with respect to x square, x, the square of derivative twice with respect to x, twice with respect to y, twice with respect to z. If I add up all of these, I am going to get minus k square, where k is the modulus of this, is the length of this vector, the wave vector, into xi. So, if we plug this into the wave equation, this term gets replaced by minus k square xi, this term gets replaced by minus omega square xi. So, what we have is, let me combine all of this. So, the wave equation was del square minus 1 by Cs square del by del t square, this acting on xi is 0, this is the wave equation. This acting on xi gives minus k square, this second time derivative of xi gives minus omega square. So, I have plus omega square by Cs square xi equal to 0. Now, if xi is 0, there are two possible ways this can be satisfied. One, if xi is 0, so you have to set the amplitude of the wave to be 0, which is a trivial solution of no interest. So, the only way that you could possibly satisfy this equation in a non-trivial way is that you have to set this term in the square bracket to 0, or what you say is that omega square should be equal to Cs square into k square. So, what we find is that the plane wave, this particular plane wave is a solution, is indeed a solution to the wave equation, to this wave equation. A plane wave like this is indeed a solution to the wave equation, provided the wave vector and the wave and the angular frequency are related. So, the wave number and the angular frequency are related through this constant Cs which appears in the wave equation. So, there is a constant Cs which appears in the wave equation. So, provided the wave number and the angular frequency are related like this, then the plane wave is a solution, the plane wave over here is a solution to this equation. Okay. So, the plane wave is a solution provided this relation is satisfied, this relation over here is satisfied. This relation, such relation between the wave number and the angular frequency is called a dispersion relation. And the dispersion relation plays a very important role in the study of waves. So, let me again remind you what is the dispersion relation. We had a wave equation, and for the wave equation we tried a plane wave as a solution. So, we took a plane wave as a trial solution and we asked the question, does it satisfy our wave equation. So, we have this wave equation, we took a plane wave like this, as a trial solution for this wave equation and asked the question, does this satisfy the wave equation. What we found is that the plane wave satisfies the wave equation provided the dispersion relation is satisfied. So, the plane wave is a solution to the wave equation provided the angular frequency and the wave number are related like this. So, the dispersion relation has to be satisfied. The dispersion relation is a relation between the wave number and the angular frequency. So, the plane wave is a solution to the wave equation provided the dispersion relation, it satisfies the dispersion relation provided the angular frequency and the wave number are related in this fashion. That is what is the importance of the dispersion relation. It tells us how the wave number and the angular frequency are related. Now, let us come back to this dispersion relation. This dispersion relation tells us that omega, the angular frequency, should be equal to Cs into k. We have kept only the positive root of this equation. So, it tells us that the angular frequency should be equal to Cs some constant into k. This straight away tells us that this wave has a phase velocity of a wave is omega by k, which is equal to Cs. Right. So, the wave has a phase velocity Cs. So, what do we learn from this? What we learn from this is that if I have a wave equation like this, then the constant which appears over here, this constant, there will be a, in the wave equation you will have a constant which appears in front of the derivative with respect to time. This constant over here 1 by Cs, we have written this constant in the form 1 by Cs squared. If you write the constant over here in this form, then this Cs which occurs over here is going to tell us the speed, the phase velocity of the wave in this particular situation. So, if you have an elastic wave which is propagating in a particular medium, we have calculated what Cs is. So, for an elastic wave, the phase velocity Cs in the medium is equal to square root of the Young's modulus divided by rho, the density of the medium. And if I have a different kind of wave in a different context, then the wave equation is usually going to be just the same as this, but we will have some constant which will appear over here, and the constant will have a different dependence on the properties of the medium, etc. But you can interpret this constant as being the phase velocity of the wave. So, let me recapitulate again for you what we have done in today's lecture. what we did was as follows. Let me recapitulate. We had an elastic rod. In this elastic rod, we introduced a deformation. So, here I show you the deformation again. We have this elastic rod. In this elastic rod, we have a deformation. The deformation moves around the elastic medium. So, if I have drawn lines in the elastic medium when the medium was undisturbed, the moment I have a disturbance, these lines have been moved around. So, this element over here has moved here, this element has moved here. So, this introduces compressions, this has got compressed, this has got rarefied, etc. The displacement of each element we denote by xi x, and the displacement varies, it is different at different points along the rod. And the question that we addressed is what governs the evolution of this xi x, and we saw that for an elastic medium the displacement xi x is governed by an equation which is a partial differential equation, a second order partial differential equation. It is the wave equation. And we could, so this is the wave equation, this xi, the displacement, follows the wave equation. We checked that the plane wave which we had considered earlier, which we had discussed extensively earlier, is indeed a solution of this wave equation, provided the angular frequency and the wave number are related in this fashion, where Cs is the constant which appears in the wave equation. It depends on the Young's modulus and the density of the medium for an elastic solid. Such a relation is called a dispersion relation. It is very important when you wish to study the wave equations and waves. Okay. So, in today's lecture we have considered a particular situation of an elastic medium, and we have studied waves in that. And what we essentially did was we derived the equation governing the evolution of waves in this elastic rod. So, we derived the wave equation governing the evolution of disturbances in this elastic rod. Now, the wave equation that we have derived here is very general. It applies in a large number of situations where we have waves. For example, electromagnetic waves which we have studied, the electric and magnetic field satisfies exactly the same wave equation. All that changes is the value of the phase velocity. So, for an elastic medium, it is the phase velocity is the speed of sound in that medium. For electromagnetic waves, it will be the speed of light in vacuum. So, for a large variety of waves, this same wave equation holds. The only difference is that the quantity governed by the wave equation that appears in the wave equation is different. For an elastic medium, the quantity that appears is the displacement. The displacement here is horizontal, longitudinal, it is in the same direction in which the wave is propagating. If you had an elastic string and you plucked it, you would have transverse displacements. So, for example, if I had an elastic string like this and I introduced a disturbance in this string, the disturbance would propagate. In this case, the disturbance is in the direction perpendicular to the direction in which the wave would propagate. It is a transverse wave. The wave that we have considered just now, the elastic wave, is a longitudinal wave. You can have two kinds of waves, transverse where the disturbance is perpendicular to the direction in which the wave propagates. Example, the electromagnetic wave, the electric field and the magnetic field are both mutually perpendicular, and they are perpendicular to the direction in which the wave goes. Transverse vibrations in a string, which I just mentioned, and you could also have longitudinal waves, which we have just discussed in today's lecture, where the displacement is parallel to the direction in which the wave propagates. So, the wave equation is very general. Our derivation here is for a specific situation, but the equation that we have derived is very general. It can be applied in a large variety of situations. The two major changes that you have to remember is that the variable changes The variable could be the electric field, could be the magnetic field, could be the transverse displacement for a string, or it could be the longitudinal displacement for the elastic wave that we have considered. So, it varies from situation to situation. Further, the phase velocity, the constant Cs that appears over here, will be different in different contexts. So, let me stop today's lecture over here. In tomorrow's lecture, we are going to discuss how to derive solutions for the wave equation.